look at some of this, but we're going to talk about why these things happen this way. For example, if we start LUA, if I said print 3, what do you think would happen? It would print the number 3. Excellent, because that's what we would think it would do. However, in Lua, there's really no reason why you can't say print equals 3. And you can put semicolons if you want. You don't have to. But I can say print equals 3. Print is not a reserved keyword. It's not special in any way. It's just a variable. In this case here, it's the variable that has a value. The value that it has is 3. Up here, it's a variable. It has a value. Its value is the function print. Right? And so up here, it's a variable that has the value. The value of this variable is the function print. And so when I say print of 3, it says, hey, call this print function like so, and print the value of 3 for me. Down here it says, okay, we'll assign the value of 3 to that print. I can use a semicolon if I want. I don't have to, though. So for now if I say something like this, when I do that, this time it'll print the value of 3, this time it assigns the value of 3, this time what will happen? Causes an error. The error is, hey, print is a 3. 3 is not a function. I don't know how to apply the function 3 to the number 3. It's not a thing I know how to do. It's because when we do this, essentially what you're saying is 3 parentheses 3. And unless we're in math and that's multiplication, it doesn't make any sense. And so in the same way that C is powerful and allows you to do a lot of manipulation, LUA is powerful in the way that you can do pretty much anything you want, like this.
How do you signify comments?
I think it's just the same as C. I think it's just, no, I'm sorry, it's not. It's 2 dashes. 2 dashes. 2 dashes make comments. Took me a second to remember what we're doing here. And so one of the things here is LUA is a higher level language that gives you a lot of control over how you do stuff. As an example, if I were to do the following, I can say foo equals print equals 3, foo print. What would happen here? It would print the value 3. Because print is a function. The value of print is a function. So the value of foo becomes the function print. So the variable foo is the function that was formerly known as print. Right? Now print becomes the value of 3, so we use the function formerly known as print on the value 3. And that prints the value 3 to the screen. Yes?
If you say foo equals, or print equals 3, how would you print it?
You don't. It's the answer. It's gone. Yeah.
Why would I want that?
Why would you want that? Okay. So one of the things that you can do is you can start building functions that then extend more functions. So let's suppose that I want to extend the print functionality, but I don't want to tell everybody that I'm going to read that they have to use a new function. So for example, let's suppose I want all of my prints to have happy faces in front of them, right? I want every time that they use the print function to use a happy face. Normally, in other languages, we would say, okay, you have to call the print with happy. Hello. And that would print the happy face hello. So I don't, this one, is that the happy face? Hello. And so it would print happy face hello, right? That's how we'd have to do it in other languages. In Lua, I don't have to do it that way. What I do is I do this. I say, my print, my happy print equals print. Then I can do the following. I can define print again. So I'm going to say function. Let me do it the hard way first. Print equals the function that takes a single string argument. And what it does, and so we'll talk about this later as well. What it does is it says my happy print of the string happy face concatenate. Concatenate is not plus and load. Concatenate is 2 periods. str. Like so. So this is a little weird. I know this is a little strange. We're talking about why all these different parts that are strange. And these languages are intentionally strange, and I intentionally show you the strangeness first for the to really break you from that habit of thinking about programming languages as if they're Java. So the first thing I do here, what's the first thing I do here?
Assign.
So I'm saving I'm saving the previous print function, the existing print function that allows me to print to the screen. Where if I lost it, I wouldn't be able to print to the screen anymore. I'm saving it to a variable called myHappyPrint. Right? So myHappyPrint is now a variable that has the print function. So myHappyPrint now prints that way. Prints the way we did before. Now I'm saying print is becoming the function that takes a string value and calls myHappyPrint with the smiley face and concatenated with the string. This is the concatenation operator. It's not a plus. It's just a dot dot. And so when now the print function, anytime anybody calls the print function, so if they say print hello, double quotes, print hello, like that, print hello calls this function here, which calls myHappyPrint with the happy face in front of it automatically. And so now every time anybody uses the print function, it'll print the happy face in front of it for you. That's why we would use that.
So you're assigning it by value, being print to the myHappyPrint.
Yes. So the value of print is now this new thing here. And really when you say it's passed by value, we're not passing by value necessarily. We can say that, but really we're passing by reference.
Okay. But wouldn't pass by reference mean that myHappyPrint points to print,
Uh-huh.
and then you change what print is,
Uh-huh.
and then it calls HappyPrint with points to itself?
No. Close, but no. So, close. So we start with print. Print is a variable that points at a function that calls print, right? I say myHappyPrint. MyHappyPrint points there. That's point. Sure.
It's the value of the pointer.
The value of the pointer. You're correct.
That's what I meant.
Yeah. Okay. All right. Just so long as we were on the same page. This is the value is a reference, not the function itself. Okay. Good. And then when I say print equals the new function, print becomes a new function down here, like so. So points at a new function. You can do all kinds of wacky stuff like this, weird and wacky stuff, using this kind of logic. You can build very eccentric stuff.
Does that mean for that, if you call myHappyPrint, it's just going to use the regular print?
Correct.
Okay.
And so what I've done is I've redefined the print function to be something new for everybody, forever. And they can do it again if they want. But if somebody afterwards goes ahead and tries to do this kind of thing, well, myHappyPrint's still going to be on top of it because this one is still the only variable that points at the actual print value. I did this syntax in particular where I said print equals this function because one of the things we want to get away from is we want to get away from functions as being different than data. Functions are data. They just are. And some languages allow us to use functions as data better than others. LUA is one of them in particular that allows us to use functions as data. Other languages don't do this as well. For example, Java, I've said before, does not do this at all, or until Java 8 did not do this at all. Java 8 now kind of does this, or it does this very poorly. C++ also does this, but it is still relatively difficult. C# does a pretty good job of allowing you to do this well. It's still difficult, but not as hard as Lua, or not as easy as Lua, but not as hard as C. So, this is just the explicit syntax. The same way that we wrote that, I can also just write the print function the standard way we kind of used to writing print functions, where we have the word, the keyword for function, the name of the function print, the arguments that it takes, and then the the scope, and then whatever it's going to do inside of here. That's also the other way we could do it. So print. So we define the function print like so. What are some interesting pieces of information or interesting things you've noticed here or gleaned from this so far? Because I've written valid Lua code except for the little squigglies. Yeah. There's no curly braces, right? There's no curly braces in Bash either, right? Bash used a different thing instead of curly braces. Bash also has scope, so does Lua, but they do it in a different way. So for example, a for loop in Bash says for something, do, what does it say down here? Done, right? The do and the done are the curly braces of C++, C, Java, right, in Bash. In Lua, we also have a do, but we don't have for a function. We have the end keyword is going to end everything. For example, in Bash it was done. How did we end an if statement in Bash?
Fi.
Fi for fee, right? That done and that fee can be like, okay, which I forget which one I used and why. In Lua, there's only one, just the word end. It ends everything. It's done. There's no dones. There's no fees. It just ends. A Lua for loop looks something similar to a Bash for loop, where you say for something, do end. Do end in Lua. Similar kind of notation. But this is still the scope notation that we have here. That we have in C or C++ or Java, which is the curly braces for us. What else?
Return statements?
So I haven't written any return statements at all. The return statements in Lua are very different than the ones we've done before. The first thing is I can return any number of arguments or any number. I'm not going to say arguments. I can return any number of return values, and it doesn't matter. So in this case here, how many did I return? 0. I could also write just the word return with nothing after it. That also returned 0 things. The same way that I return 0 things, I could also return 1 thing by saying return 1. If I wanted to return 2 things, I'd say 1, 2, 3, 4. How many things did I return there? 4 things.
But then if you call print,
It would call my happy print, which is the print function, which makes the happy face in front of it. So when they call hello, it would print that with the word hello in front of it, or the happy face with the hello in front of it. And then it would also return 1, 2, 3, 4. Like the numbers 1, 2, 3, 4. Right? Why would we do this? I don't know, but yeah.
Is it possible to like do a loop and return a
So so you can't have a return. If you want to have a loop generate a bunch of things to return and then return them all at the end, the answer is no, you can't do it with the return statement in the loop. You can concatenate a bunch of stuff together and return them at the end. Which leads us to our next question is, there's only one data structure in Lua. There's no such thing as an array. There's no such thing as a hash table. There's no such thing as a linked list. There's no such thing as a struct. None of those things exist inside of Lua. The only thing that exists inside of Lua is a thing called a table, which is, it's almost a bidirectional hash table, which is, if you don't know what a hash table is, it means that it can store anything and use anything as a key. It's not that there's no types, it's that this language is loosely typed. When we say something is loosely typed, it means the variables do not have a type, but the values do. So let me give you an example of this here. So in Lua, let's suppose I have a variable. I can say, for example, x equals 3. When I say x equals 3, that value 3 has a type. What is that type of that value? So it's a number, right? Are you looking it up? No? Good. Lucky. So we think about it as an integer because that's the way we think about this, the programming languages. For Lua, that's just a number. Integers and numbers are not, they don't distinguish between the two of them. Which leads us also, if I then say x equals 3.14, that's also valid because 3.14 is also a number. Does x have a type in either of these cases? No. X is typeless, however the value is typed. So the value for both of these cases is 3.14, is number, sorry. LUA doesn't allow you to do things like concatenate strings and numbers. So for example, if I said y equals the string pi, like so. If I tried to say z equals y concatenated with x, like so, LUA is going to say, I don't know how to do that. It's not something you can do. You also can't say y plus x. It's also another thing that you can't do. Y plus x doesn't work. Because strings plus integers and strings plus numbers don't make any sense. There is a two-string function. I believe it's just str. I think you can call str and x, though. That turns any value into a string, and that allows you to concatenate strings together. So if you wanted to do this concatenation, even though you couldn't do this, you could say y dot dot str x. It might be two-string, but I think it's just str. That function string or two-string is not a special function. It's the same way with print. If I wanted to override it, I could override it so it would do something else. I could change it. I could change its value to be a different function if I wanted to. Just depends on how you want to implement stuff. Yes?
Is LUA interpreted?
LUA is an interpreted language. The first assignment that we'll have with LUA is you're going to write a LUA interpreter. Yeah. When we start that, I go, oh, that's really hard, but it goes in very well with what the next topic is, which we're going to kind of go into now. Actually. Any other questions? So one of the things when we start looking at LUA, when we start talking about LUA, is one of the ways I like to say it is LUA doesn't care. It's kind of like C. C doesn't care what she's like. C with the C compiler, you can say one kind of value equals another kind of value. The compiler might be like, those aren't the same thing. If you typecast, it's like, all right, you know what you're doing, even if you don't know what you're doing, right? LUA is the same kind of thing. LUA doesn't care. You can change its variables to whatever it is. You can change their print functions. You can delete things. You can get rid of all the stuff. For the most part, LUA lets you do whatever you want to do. However, the two languages have very different purposes. One of the things that LUA does that C does not do, as an example, if we had a LUA table, it's something like this. A equals, and the curly braces mean table in LUA. 1, 2, 3, for example. This creates a table of 3 elements long. We want to think, if you want to, you can consider this to be an array of 3 elements long. If I wanted to print that number, let's print that number 2 there. I would say print A of 2. That'd be the second element. What's the second element in C? Which index? 1. What's the first element? First element in LUA is 1. Second element is 2. Third element is 3. What's LUA for and what is C for? C4 explodes things. But. So we know that C is for programming applications. It's for building code that has to be run very quickly. We know that it is used for operating systems. We know that it is very low level in the sense that you have a lot of control over the machine that it's operating on. So what's LUA for then? They both share this kind of commonality of not giving a fuck what you do with your code. But what are the different? They're designed for different people.
LUA's more like scripting.
It's true. LUA is a scripting language.
Is LUA coding for like a purpose? Or
So-
like science, I guess.
Okay, good. So LUA is not actually for science. That's a good idea, though. LUA is for a different purpose. It's actually the purpose that LUA's original purpose was for dams, but they controlled hydroelectric plants and dams, but it's been since used in many other places.
Engineers.
So not necessarily just engineers, but you're on the right track. One of the things here is LUA is designed for non-programmers. That's who LUA is designed for. C is designed for software developers, for programmers. If I asked an engineer who had never programmed before to program in C, they might be able to figure it out, but they wouldn't necessarily have a good time. They definitely wouldn't be able to do anything useful with it, or particularly useful. LUA, on the other hand, is designed specifically for people who do not have a lot of programming experience, and it's designed such that they are able to quickly and effectively do very powerful things. This is the reason why they allow you to do this kind of concept here. If I came to you before you had learned any programming, and I said, I have a print function. I want to be able to temporarily store that print function in the variable temp print. Temp print equals print. I want to temporarily store that function in that variable. If I'd asked you this when you first started, you'd probably go like, sure, why the fuck not? Right? This is something that makes sense to people in general when we learn about variables and stuff from mathematics. If I say that I have a variable x equals a, and then I also know that a equals 3, I know that x is going to have the value of 3. That makes a lot of sense to me. Regular people don't think about the difference between 3 and 3.14. Those are both numbers. Who cares? Why do I have to learn about integers? Why do I have to learn about the difference between floats and integers? I don't want to know that. I want to be able to say those two things are the same kind of data, because they are. The other thing that comes up happening is when I say, or when we do common things like a is a function, a is, or not a, let's do another variable here. Let's say y equals the integral from 0 to 2 of x squared dx, something like that, right? That's saying that y is that function, right? Because the integral is a function. We learn about mathematics, we go, okay, yeah, so y is the value of that function. If I then take these 0 and the 2 here, and I get rid of these 0 and I 2, and I put two unknowns in here, like I and j, yeah, I to j, like so, people inherently kind of understand, oh, I can replace I and j with any value, and I can calculate that function, and then I'd be able to know what the value of y is. This is kind of an inherent way that people function, and so this concept of being able to store functions as variables, like that, this is the intuitive way that people approach problems. Not all that crap that we taught you before, right? And so what it is LUA is everything that you thought programming should be. Everything you thought you should be able to do with programming when you started, LUA can do, right? The problem with this is, when you're not careful about this, LUA explodes in your face. Because when you try to solve things in an intuitive way, like, oh yeah, hey, I can do this and do some, and you forget that you've done this, and then you just print 2 weeks later and it prints out the smiley face, you're like, fuck, I forgot I did that shit. Whereas other languages are more explicit and they force you to remember these things. The compiler goes, no, you can't do that. Not going to let you. So the compilers allow you to build longer-term projects, whereas LUA on a long-term project is difficult if you're not paying attention. Does anyone know the most common use of LUA today? Video games. Blizzard uses LUA almost exclusively for all their video games. Diablo 3's user interface and graphics are almost entirely written in LUA. Warcraft 3, WoW. WoW is the biggest game for a long time. There's a number of smaller game studios that almost exclusively use Lua for their programming now in terms of user interface and programming and scripting. Some of the bigger studios like Rockstar have their own scripting languages that are like Lua, so they don't implement their own. But other up-and-coming studios have implemented Lua as their scripting language of choice. The only large competitor that doesn't use Lua right now, that's kind of free to people, is Unity. Unity uses C# as opposed to Lua. Although Unity tried to push what they called BooScript, which was a version of JavaScript, and Lua kind of, and then everyone said, no, I don't want to learn both of those. And so that failed, but kind of. So that's what we're kind of getting into here, is we're going to throw away this concept of functions as being static things that don't change. We're going to throw away this concept of variables have specific types. We're going to throw away this concept of that we can't know and use things the way that they're intuitively supposed to be done. Which brings us to the next topic is, if Lua can do this, and this, and all these other things that we've been talking about, why don't other languages? Some of it is overhead. Lua has more overhead than a lot of languages.
The ability, the functionality of overloading functions and polymorphism
Mhm.
is limited when you use a loosely typed language.
Ah, so this is one of those things. Is we're gonna when we start programming Lua in earnest, we'll actually implement polymorphism and inheritance in about 12 lines of code. Throw that idea out the window. Oh, polymorphism and inheritance are hard. No, they're not. They're actually really, really simple. We just don't recognize them as being simple.
How do you overload a function if you don't have a specified number of return types? Well, you overload a function by sending different numbers of arguments to it.
Lua doesn't care how many arguments it returns or how many arguments it takes.
You can't overload the same function.
You can't. So we'll do this. We'll do this part later. Like, so why is Lua allow us to do this? And part of it is the overhead is given to us.
So the only data is the table. So
That's the only data structure is a
Yeah,
table.
so it's all tables.
Everything's tables. This table's all the way down.
Well, yeah, you might have like something where you send in one variable or one number and it does something different than if you send it two numbers.
Uh-huh.
You overload that function to have multiple function definitions for different arguments, sort of like constructors. That's what I was thinking.
And so that is how all the rest of the programming languages do it too. They just do it for you with the compiler stuff. We'll talk about that later. So,
Is there a problem with reusability?
what do you mean by reusability?
Well, we've got a big company, we're all coding on this one project, and people do stuff like this, kind of hard to keep track of.
So yes, and so one of the things that happens with Lua is Lua's other big problem or big part of this is everything in Lua is global unless you specify otherwise, which is the opposite of every other language. And so when you're working in a big project, unless you have very small compartmentalized projects or parts, then the scripts, the variables, and the functions override into other places, and it's difficult to work in a larger team. When you work on a big project, what ends up happening is you have one set of Lua scripts for one particular task. So for example, when they're doing the hydroelectric dams or something like that, what you have is you have one Lua script that's in one Lua environment. There's only one set of it that runs one part of that turbine. And another Lua script runs another part of that turbine. And another Lua script runs another one. And those three Lua scripts are not influential on each other at all. And so we separate them more completely. We sandbox them away. But so why don't other languages do this stuff? And so part of it is that we don't want is that it's that we build in protections to work with larger teams. But what's the other reason? Are there other reasons? How do programming languages work? And that's ultimately what this class is going to be all about. How do programming languages work? So let's look at a language that we're more familiar with. Let's look at C. And let's take a gander at it and see if we can figure out how it's working and why. Those are two pretty common instructions, relatively straightforward, right? What does it do? It doesn't print X as 3, it just prints the value 3. Oh, okay, yes, you're correct there. So what's this first line do? X becomes the value of 3, and then this line prints the value to the screen. How do we know that? We know that through experience. We've memorized some things. Let's look at this first line here. What have we memorized? What have we learned as a collective or as individuals?
Time.
So we've learned that there's a bunch of things going on here. I see, I don't know, maybe 10 things that we've memorized that have come to pass for us. For example, what does this mean?
Assignment.
That's assignment. What's this thing?
Variable.
So the name, or the identifier, or whatever you want to call it. What's this?
Type.
Type. What's this?
Value.
It's a value. And that value also contains within a what? A type as well. There's also a type associated with it. What's this thing? End of command is really what this is. End of command. What else are we missing? More stuff in there. Well, so we know that's what assignment means. So we know that there's going to be a memory allocation inside of here. There's a big thing here. Probably the single most important one. Maybe the second most important one. So the end of the line, so the new line character after the semicolon? So that actually doesn't matter because the semicolon is the end of the command. I could actually write these both on the same line. You're on the right track though. Let me try writing that again. It's the spacing. We don't even recognize this when we think about it, but if I tried to write that instruction again, if I said the following, if I wrote the following, is that valid for C? No. Why not? So does this space matter? No. Does this space matter? No. So neither of these matter. Which space matters? The first one there, right? So why does this one matter and those two don't? And how do we know that?
Experience.
Experience, right? Okay. So I know that GCC, or the new C compiler, that turns this from a source code into something that runs on a computer, I know that GCC is a program. Therefore, there is a program that knows that too. How does that program work? How does the GCC, or the new C compiler, know? How does it semantically know that all of this information in there? That's the question we need to answer. So let's see if we can do this. Let's see if we can write. Let's see if we can write some pseudocode. We'll approximate C or something along those lines. That would be able to break this, not even the second one. We're not even to that part yet. Let's see if we can write some pseudocode that would break this very first instruction down to what it means. How do we start? So if I was going to do this, I'd have to read that line. So let's pretend they're typing that line in on the keyboard, right, on the terminal. How would I get that line of text in, first of all? I would scan F. So I'd say I'd have a char array, which would be the line. Let's go ahead and give them 256 bytes. And then I would say scan F with a %s in the line. Now, would that %s work for this line here? No. What does that %s give us?
String.
Just the first part of that, the first word. That first space would break it, right? So do I know how to do this for an entire line? What is it, you know? So it's a %. I believe it's, yeah. So let me write that bigger so everybody can see it. It's a funky notation, but it allows you to read an entire line. So it would be a %, left hard bracket. That's supposed to be a left hard bracket too. Left hard bracket. Upper caret, thank you. Up caret, // // lowercase n, right hard bracket, like so. That says reading an entire line. So that would read in that entire line there. So that would give us that entire line. Does that actually break us or stop us on that semicolon there? No. So, the scanf really isn't going to work for this line because really we want to end at that semicolon, but we'll leave it away for now. Okay, so now I have this line, right? How do I check to see if that's what's written such that I know that's what I want to do semantically? I need to be able to cut this up into my white space, right? What is the white space in this case? There's a special word for what we're doing here when we cut stuff up. It's the delimiter. So for our C instruction, the delimiter here is white space. There's also another delimiter. What's the other delimiter? The semicolon and the equal sign. Those are the three delimiters on this line, right? Let's think about this. Is it always true that it's those three delimiters for this line? Could we, let's not necessarily for this line, is there any a time that a semicolon is not a delimiter? Let's see. So you put it inside quotes. There's one time. We can also put it inside single quotes. Right? So when we're saying, I'm gonna write a magic line. I'm gonna say parts equals. I'm gonna split this. Split on delimiters. Now, split on delimiters obviously isn't a C function, not yet anyways. But we'll just go ahead and pass in the line to split on the delimiters. We get all the parts there. But the delimiters obviously aren't just the semicolon, right? We have to figure out how to split these things. This stuff here. This figuring out how to split things has a special name. It's called tokenization. So to tokenize something, or tokenization, what does that mean? Tokenize or tokenization? What does this mean?
Split something into parts.
Split into component parts. Component in this case refers to the smallest viable subset. So if you split this into a smallest viable subset. If I was going to tokenize this int line up here, what would the tokenization look like? What's the smallest viable parts? Sorry? So we could say individual characters. Now this isn't, so the characters are not the smallest viable part in this case here. We could split them up into characters, but for example, is the split of I and TE more informative than the split of I and T? Which one of those splits is more informative? That one's more informative than that one. Correct? The reason why we don't just split to the smallest component is because I know that the I character is actually 0, 0, 1, 1, 0, right? Why don't I split it down to the individual bits? Because the individual bits are not as informative as the letter I. The letter I is not as informative as the word int. So the smallest viable component here is the word int, not the letter I, not the individual bits. We know that we can split this word I into int, so the component letters, or we can split it into the binary, but it's not particularly useful for us. We have to figure out where we're going to split it to. So we're going to split it to the int word. we split to int. So we have the int. What else? The x. The operator. Value. And the end command. And we're going to leave the end command off for now. And the reason why we're going to leave the end command off is the end of the command means that this is a complete instruction. The semicolon isn't particularly important for the instruction. The instruction is actually this. That's what the instruction actually is. So when we split it into parts, we're not going to split on the delimiters just exactly. We're just going to tokenize that. So we can say tokens equal tokenize the line. How we actually go about tokenizing the line is obviously going to be important. So for example, that semicolon is different than that semicolon, which is different than that semicolon, which is different than that one, which is different than the equal sign, which is different than the white space. So there's obviously going to be a lot of work that goes in there. But for shits and giggles, how would we implement tokenize? What would I do inside my? What would that tokenized function look like?
Like having a realistic code using
So I see. So when you say you have an array list, you have a set of those. So you have a bunch of delimiters, is what you're saying? Okay, so then how would you find a delimiter or something inside the line? So it's not just white space, obviously, because the assignment operator is a split and the semicolon is a split as well. So how would we do that? And the answer I'm looking for is I'd have a for loop of some kind that would loop through this string here. And then I'd have a bunch of if statements inside that for loop that would look for individual parts. If it found something, then I would split it in a certain way. So I have a for loop with a bunch of if statements. That's essentially what I would do inside the tokenized function. Those if statements might be exceptionally complex. For example, how do I differentiate this semicolon, that semicolon, and that semicolon? Different if statements. A bunch of different kinds of if statements. We have to figure out, well, for example, if I had hello semicolon, like so, I have to be able to know that that semicolon doesn't matter. And so I have to figure out how I'm going to separate the fact that I have a string. Which kind of, what do you think these double quotes mean? What is that? It doesn't mean ignore me. It means something else. I'm a string. What were you going to say? So this guy here and this guy here means this is a special value. Here I said value was this 3, right? What kind of value is that? It's an integer value. What kind of value is that hello?
String.
String. This, yes, okay. So this string value here and this integer value here get tokenized the same way. Once we're done with tokenization, we want to be able to do something else. So for example, if I take the line int x equals hello semicolon with a semicolon at the end there. Let's suppose that's the next line. Is that a valid line? No, it's not valid. However, the tokenizer doesn't know this. The tokenizer's job isn't to figure out whether or not this is valid. how would this line be tokenized? We would get int, we get the box for the int, we get the box for the variable. So instead of x here, what should I'm going to put variable here. Instead of x, we can call it variable x. We have the assignment operator. So instead of the equal sign, I'm going to call this an operator. And this is going to be the assignment, or I'll just say operator equal sign. Like so. And then over here, this is going to be a value, and it's going to be a string value. And that's going to be the entire tokenization. Like so. That's the tokenization of that guy. After we've done the tokenization, we want to be able to then identify that this is invalid. This step is called lexical analysis. Lexical analysis. This stuff that we're talking about today is not going to be on the test, by the way, just so you know. This is moving forward stuff. Lexical analysis. Lexical analysis is going to be checking to see whether or not this is valid or whether or not this is valid. What is this equivalent to in English? Or in any language for that matter? Sorry?
Grammatically correct.
Grammar. So we're doing a grammar check. So somebody else said spell check, right? Spell check is kind of like tokenization, and then there's a little bit after lexical analysis as well, whether or not we're going to do spell check. But grammar check is really the lexical analysis here. The grammar of the language is defined by the lexicon. And when we talk about lexicon, what does that mean? What is the lexicon of a language?
All the words that make it up.
And their way and the structure they can be put together in. So, for example, in English, English is a subject-verb-object language. So, for example, in English we say, Billy kicks the ball. That's the sentence. So Billy kicks the ball, right? How do we know that this is grammatically correct? Well, we have a subject, verb, object. And we know that English subject, verb, object is acceptable because of the way we're doing when we're doing a lexical analysis, grammatical analysis. Other languages, like Japanese, for example, don't go this way. They go, it can be subject, so it would be Billy, the ball, kicks. Like so in Japanese. Because Japanese is a subject, object, verb language. Subject, object, verb language. In Japanese. Other languages do it differently. For example, Spanish. How is Spanish different than English? What's a common difference?
The adjectives go after them.
So in English we would say, Billy kicks the red ball. Would you say the same sentence in Spanish? Would you say Billy kicks the ball red? Right? And so in Spanish it would be Billy kicks the ball red. Which when you say that Billy kicks the ball red in English, that's a weird sentence. Right? The sentence means it takes on a different meaning. These grammars, or these lexicons that define the languages that we use, is also the way that we do lexical analysis for computer programming, for programming languages. For example, when we're looking at this thing here, if we make it a little bit simpler, if I say x equals 3 versus x equals low. If we don't know the type of x prior to starting this, which one of these is correct? We don't know the type. Do we know? It could be either. We don't know. But will the compiler allow both of these to happen at the same time? And the answer is no. Because the compiler, when it's doing its lexical analysis, knows the type of x. So for example, in a lexical analysis of this part here, if I said, for example, int variable operator assignment int value, that's a valid sentence in C, right? I can also say string variable operator assignment string value in C. Both of those are acceptable sentences, correct? What do I need to know about x before I can do either one of these things here? If it's going to be an integer or a string. So we start breaking these down. When I see this, what do I know about it? I know that I have an int variable. I know that I have the assignment operator, and I know that I have the string value. Can I do that assignment? The answer, the compiler is going to yell at you about this. The compiler is going to be like, well, no. Can't do that. The compiler is going to yell at you because it doesn't match one of these two valid sentence prototypes. And so the grammar is wrong. What I'm going to try to do now is I'm going to try to demonstrate this for you guys with the compiler. We're going to look and try to see if we can find the difference between when the lexical analyzer fails and when the tokenizer fails. So we're going to start with a very simple C program. What we're going to do here is we're going to say int x equals 3. We're going to start with something that works. We're going to do the printf %d with the new line with the x here. So I'm going to go ahead and do the GCC here. GCC test.c. Okay, I don't know why that took so long. But test.c compiled successfully because all these are grammatically correct sentences. They're all syntactically correct. They're all tokens correct. So let's change this. How should I change one of these two lines such that the tokenizer will fail? So that's not going to be the tokenizer. We want to fail the tokenizer, not the lexical analyzer. So we put the int and the x together like so. Let's see if that'll make the tokenizer fail. What does this say down here? It doesn't matter if we return 0 or not. If we for the test here. What's that say? int x is undeclared. This is not a tokenizer error. for example, if I had said like so, int x equals 3, oops, let me comment this out real quick. Int x equals 3, one more time. Int x equals 3 is not a token, does not fail the tokenizer.
Maybe a colon instead of a semicolon?
What does this mean? Syntax error before colon there. Does that error look different than the other ones we were looking at before? Right? Let's see if we get rid of this int, if I do something else like this, if I do int, is that going to cause a tokenization error? Is it going to cause an error before the, right? Makes it the undeclared error again. What happens if we say int x equals the string hello? Let me do that. Just gave me a warning. This is okay. Let's do let's do 3.14. Let's see if it'll let me do that or not. It'll fail me on that. Nope, it'll let me do that too.
3Y.
Huh?
Read a letter. 3Y.
3y. Invalid suffix y on an integer constant. This is actually tokenization error right here. This is the first one. All the rest of them are the lexical analysis errors. It's the first one we managed to happen. What happened is it tried to tokenize that number 3. As it was trying to tokenize that number 3, what it did is it tried to figure out if that's an integer or a float or a double or what kind of value that is. And when we do floats, for example, we say 3f to make that a float. That's the syntax for the tokenizer, makes that a float. Oh, no. Integer constant that time. We'll put 0f there. Okay, there we go. So those errors we were seeing before, let me just go back up to them. The invalid suffix, those guys, these are the tokenization errors. These are ones the tokenizer is failing. The tokenizer has already correctly tokenized that 3 to an integer, or incorrectly in this case, and then it tries to put the f on the integer constant, which fails it. Then when I do that 3.0 there, and I put the f on it, what it does is the tokenizer says, oh, 3.0 is a float, or a double, and I put the f on it, it turns that double into a float. When I say int x equals 3.0f, the compiler obviously lets that happen, because the compiler didn't throw any warnings there. If I do let's try a warn all, let's do a w all. Capital W. No, it didn't even when I told it to warn everything, it didn't say, hey, that float's going, or that double's going into an integer there. So apparently, according to GCC, an integer equaling a double is totally acceptable. Which is unfortunate for us, because that would cause us an error later. But it does warn us about the other one there where we have that hello, right? Because the assignment makes an integer from a pointer without a cast, right? So this warning here is the lexical analyzer giving us the warning. Earlier, when we had the int x is undeclared, that was also the lexical analyzer. So, or the when we take off that integer declaration, it's the lexical analyzer says, hey, I don't know what the type is for int x. I don't know if I can make that assignment. So. What do we want to do after we do lexical analysis? what's the next step? Hmm? So execute. So we're going to say execute or code emission. That's the other option. After we do our lexical analysis, we want to be able to do either code emission or code generation. / interpretation. The other word for interpretation is eval or evaluation. So we're going to do code generation or interpretation / evaluation. And so when we talk about interpretation or evaluation, that's when we're talking about what kind of language? So there's two kinds of languages. C is one kind, Bash is another kind. What's the difference between the two of them? What is it? Scripting versus compiled, right? So if we do interpretation, that's a scripting. What's the other name for a scripting language? An interpreted language. That's where that word comes from. Code generation is when we actually generate the assembly language code or the ones and zeros that would produce the desired behavior. So we either have one of those two offshoots. For the most part, we're going to only talk about the interpretation. We're not going to talk about how to do code generation. If you know what the Dragon book is, the Dragon book is this book here. It's how do we do these steps and the code generation. That's an entire, maybe even maybe 32 weeks of material is that section there. Fortunately for us, this section here on the other side is probably about 7 weeks of material or so, and so that's what we're going to cover. We're not going to delve too deeply or delve too deeply in how to do interpretation, but we may be able to do some at the end. So let's draw it again with a different picture. I've used all the whiteboards. Source code comes in. What happens to the source code when it comes in? What's the first thing we're going to do? We're going to tokenize it. For now, when we're thinking about tokenizers, we want to think about essentially a loop of some kind that has a bunch of conditionals inside of it. If a certain case is met, do a certain thing. Else if another certain case is met, do a different thing. Else if another case, do a different thing. The result of the tokenization, or the tokenizer, is a set of tokens. After our tokenization, what do? We do the lexical analysis. And lexical analysis does what? Checks for grammar. The output from the lexical analysis is either a valid set of tokens or nothing. There's no two of them. You either work or you don't, one of the two. So we know the output from the lexical analysis is a valid token string. Valid token stream. When we say valid token stream, we mean they are grammatically valid. We do not know if they are conceptually or semantically valid. And this is the hardest part, is when things are semantically valid or they actually do what they're supposed to do. So for example, if I wanted to add two integers together, if I had integer x and integer y, and I said z equals x minus y, is that semantically valid to add two integers together? Nope. Will the lexical analyzer ever be able to figure that out? No, because that's valid. That's a valid sentence. I can subtract two things. grammar doesn't give you meaning. It only tells you that the sentence is coherent. It doesn't mean that it doesn't tell you anything about the sentence. For example, when we were doing the Billy kicks the red ball thing, the sentence in English, Billy kicks the ball red, means has an entirely different meaning than Billy kicks the red ball because of the way English. Both of those are grammatically correct, but the meaning and the semantics are different between the two of them. Lexical analysis will only tell you if they're grammatically correct. It will not tell you if the meaning is as you intended. This is the reason why many times your programs will compile and run, but they do not produce the correct output. They don't produce the correct output because the meaning is wrong. What you expected the meaning to be is not correct. After we have the valid token string, we're going to do evaluation, and this is probably the biggest step. Evaluation. And this is the step that actually runs the code, or this is the part that makes the code actually execute. So we talk about, when we talk about in LUA, we are going to do evaluation. When we implement the LUA, when we say we're going to implement the LUA interpreter, we're not going to do any of these steps. The LUA interpreter itself does all of these steps for us. We may only have to do a little bit of tokenization and lexical analysis. We might only have to do a little bit of it, not much of it.
So we're not writing a LUA.
So you're right.
Okay.
Yeah. So what we're going to do is we are going to write a C program that will interpret Lua code, right? And the C program that interprets Lua code takes about 20 lines of C. That interpreter will not allow you to do for loops, and it won't allow you to do anything that is multi-line instructions, which would require that you do some tokenization and some lexical analysis as well. But once you implement those two things, which take about another 20 lines of code or so, you have a full Lua interpreter. Yes. So when we talk about doing all these steps, one of the first things we said is, well, we have to do this scan, right? And then we gave up. This is what we're going to do in C as well. We're going to do a scan, and then we're going to give up. And fortunately, all of these steps, tokenized lexical analysis and evaluation, is going to be done by the LUA libraries that we're going to be using, the LUA environments that we'll be using. Why did we give up at this step? Why did we kind of stop and just start drawing pictures and not more code? That concept of tokenization is hard. This concept of lexical analysis is harder. And this concept of evaluation is possibly hardest to do all these parts. So to tokenize, lexical analyze, and then evaluate stuff is very difficult. The concept is simple. We want to be able to break all these steps down. But we have to think about how many special cases are there in C for tokenization? 1,000? 2,000? Think of every time that you've ever been like, oh, I forgot my semicolon, or I should need an extra space, or do I put it in space here? Is this a comma, or a semicolon, or a colon? And the exclamation point means what in Lua? Left parenthesis, I forgot my right parenthesis. How many times have you done something stupid over the course of starting a program? Think about that in Java, C, etc. That's most of those stupid things, like the semicolons, are this tokenization step. Not even break this step here. The lexical analysis step is also difficult in the sense that how do we only talked about getting to this step. How do we grammatically, we talked about the fact that we have a grammar, but how do we validate that that is valid grammar? How do we do it? For example, if I give you an English sentence, Billy eats potatoes, how do you know that's grammatically correct? What steps do you as a human take? Experience, right? Do computers have experience?
Yes.
You can argue that case, but at the lowest level, do they have experience? Like, I mean, no. How would I get a computer to validate this as an English sentence? as English grammar?
Nouns and verbs.
I would have to be able to say, okay, that's a noun, that's a verb, and that's a noun, right? Why do I not say Billy eats Billy? That'd be noun, verb, noun, right? Billy eats Billy, is that a valid sentence? Oh, shit. Huh? There could be two Billies. One could be dead, the other would be eating it, right? Doesn't have to be dead, I guess, you're right. That takes an entirely new meaning. Right? Those semantic means that we are able to do, experientially. I see why you started laughing. Anyways, when Billy eats potatoes, it's a different thing. We have to be able to say, we have to be able to map every single English word into. We have to be able to map every single English word into a type. So, for example, we say, cows eat grass. How do we know that cows is a noun? And then we'd have to have verbs, and we could say Billy eats cows. And how do you know that that's cows are nouns? It's okay. We'll be done here in a second. So how do we do this? How do we do this lexical analysis stuff with code? Why is it that the C compilers and the Java compiler is so incredibly finicky about these things? Why is it that I can't use a capital I in my int? Why does it force me to use the lowercase I? Why do you think? Because when it was doing this tokenization or this lexical analysis step, the person who implemented said, fuck that, I don't want to do both of those. I'm only going to implement enough so that lowercase I works for int. And once I've done that much work, I'm not going to allow any other syntax to be valid for that. That was a conscious decision that somebody made in this step here. Why did they make it in that step? Because these steps are hard. Why make it even harder? Sometimes when you say, why doesn't it know what I want it to do? The answer is because it's stupid. That's all it's doing. It's doing this step and that step. That's all the compiler's doing. And then it does this magical evaluation step, which we'll never cover. Well, the code generation stuff. But this tokenization, this lexical analysis, computer programs are dumb. They're not particularly smart. Oh, it should know what I'm doing. No, it shouldn't. You just didn't write the right text for the tokenization to work. Or you didn't write the right sentence for the lexical analysis to work. It's not smart like we are. We have to conform to its grammar, not the other way around. We have to try not to cannibalize. All right, we'll be done for today. If you have any questions, let me know.